Hello, Health Science 4502 students. This is Professor Van Dyke with your lecture for the week 11. We're talking about particulate matter, and so you'll notice that with the PowerPoint, this was generously loaned to us by John Hopkins, Bloomberg School of Public Health. So this again with the PowerPoint presentations, I hope everybody's able to follow along with them. I know there's a lot of very complex materials on this particular presentation, but the main thing is that the takeaway from this is that particulate matter can be very harmful in an occupational setting, but also in a personal setting as well. So when we think about particulate matter, we tend to think about things like bronchitis, emphysema. We tend to think about bronchial issues, but you can also think about things like nasopharyngeal cancer with people that work with sawdust and things of that nature as well. So we're going to go ahead and move through this. I apologize. I'm going to try and keep you posted on the slide number that we're on, but we're going to move into section A, which is the introduction and definitions. So the first definition is essentially what is an aerosol, and this is a substance that is stable. It can be a solid or liquid particulate in the air. So some good examples of an aerosol can be cigarette smoke, welding fumes, or even sea mist. So you see it kind of runs the gamut when we think about solids or liquids that are particulates in the air themselves. So there are a lot of examples in regard to aerosols. On to the next slide. So types of particulates. So this is slide 5 now. So we have dust, which is a solid aerosol generated by handling, grinding, abrasion, or cutting of bulk materials. So when you're cutting into things like, as I had mentioned before, like wood dust from cutting into wood, but certainly from abrasions, like sanding things and grinding them on a grinder. These can generate dust. So dust particle size is related to the amount of energy that's involved in creating that dust. So the higher the energy is, the smaller the particulate matter. And you're going to find this fairly consistently with a lot of the future terms that we're going to discuss, that if you have a higher amount of energy that goes into creating that dust, it's going to be much smaller in size. So some good examples of dust, we talked a little bit about sawdust, but you also have coal dust as well. So you think about the amount of energy that goes into making those two different things. So with sawdust, there definitely is a high RPM in regard to the blade that's cutting into the wood. But when you imagine like with coal dust is usually going to be a much smaller particulate size because it has a much higher energy to generate it in what's actually going to make that coal dust actually appear. But again, both of these can utilize high energy sources that can make very small particulate sizes in these dusts. On to slide 6. So types of particulate aerosols. Again, these will be mists. So we talked about dust. Now we're talking about mist. So mist is a liquid aerosol that's generated by condensation from a gaseous state or by the breakup of bulk liquid into a dispersed state. So you're going to have this process upon which it's generated, and we're looking at droplet size now as opposed to like with when we were talking about dust. The droplet sizes are going to be related to the energy again. That's the amount of input that is generating dust and fibers. So good examples of this are going to be metalworking fluid from a lathe, paint spray, liquid mixing operations, and things like that. So you can see the difference between mists and dusts, that essentially when we're talking about mist, we're really talking about these droplet sizes that are from these liquid aerosols that are generated by that condensation process. So on to slide 7, we'll talk about smoke now. So again, you can see, with regard to smoke and dust and mist, that the amount of energy that goes into them will be indicative of the size of the particulate matter itself, that suspended component within the mist or the dust or the smoke in this case. So smoke is a solid aerosol resulting from the incomplete combustion of carbonaceous materials. So you really see smoke, for instance, you see tobacco smoke. That's that incomplete combustion process, and what actually is remaining is that smoke component. So you also see this with burning firewood and things like that. and a wide range of particulate sizes. So again, higher efficiency in the burn is going to have a smaller particle, and lower efficiency is going to have a larger particle. And some examples of that are wood smoke and diesel exhaust. So again, the higher efficiency the burn actually is, it's going to generate much smaller particles. And this is slide 7. Let's move on to slide 8, which is fumes. So these are going to be solid aerosols that are generated by the condensation of vapor or gases from combustion or other high temperature processes. And again, as you remember, fumes, they can be very dangerous as well in regard to generation of particulate matter that can be breathed in. So these are usually very small, and they're going to be spherical in nature. And some sources for fumes, we can have welding and foundry and smelting operations, or hot cutting or burning operations as well can generate these fumes. So if you've ever welded or been around welding, you can see these fumes that are being generated, very small and spherical in nature, and can be fairly dangerous when you're breathing them in large quantities. Onto slide 9. Again, this is another type of particulate aerosol. It's called a bioaerosol. So again, we're just kind of giving you an overview of different types of particulate matter that can be breathed in. These are solid or liquid aerosols from biological sources, and you'll definitely see the difference here, because we're going to be talking about things like viruses and tree pollen when we talk about these bioaerosol sources. So they can be infectious, they can be allergenic, and they can also be very irritating. So certainly tree pollen, things of that nature, when you breathe them in, they can be irritating, and they can be really do some stress in regard to breathing things in. You can really see these with the pollens, but you also see them as well with things like mold spores, animal allergens. So when you see someone who's allergic to cats, they're essentially breathing in these allergens, and they can be very irritating, and we call these bioaerosols. So on to fibers. This is slide 10. This is a special, based on toxicological properties, kind of dust that is fibrous in nature. So what you're looking at here is something that's longer than it is wide. And think about things like asbestos. Asbestos is a great example of a fiber that can be breathed in. It can be very problematic for individuals. So you're familiar with asbestosis. You're familiar with mesothelioma as well, I'm sure. So aspect ratio, length to width, is defined as a 3-to-1 or 5-to-1 ratio. Toxicity is a function of the composition, size, and number of the fibers, and a good example of that is that asbestos. But you also have fiberglass as well, or refractory ceramic fibers that can be generated, and these things are and then breathed in, and they certainly, as you know, if you watch much late night television, how dangerous asbestos actually was for the individuals that were breathing in these fibers. But again, you look at these small differences between what essentially is going to make this particulate matter different from an aerosol, a bioaerosol, a mist, a smoke, things of that nature. So you can see these small differences. On to slide 11. When we quantify aerosols, we're looking at concentration is going to be equal to the mass of the contaminant over the volume of the air. And then we're going to measure these typically as micrograms per meter cubed or milligrams per meter cubed. And certainly something that we generally tend to look at. It's a very simple it's a simple equation, but again, for purposes of the class, I'm not going to have you generate equations for concentrations. The main thing for me is that you have a takeaway in regard to how dangerous these things actually can be, but again, that there are differences between mists and smokes and things of that nature, that you have that understanding. On to slide 12, moving into section B, which is particle size. So this is going to discuss the particles themselves. So you're familiar with PM 2.5, which you've discussed in previous classes, PM5, PM10, and these are those components in regard to how they're going to behave in regard to aerosols and things of that nature. So the airborne behavior, such as settling velocity, is going to be a function of its size, specific gravity, the shape of the particles. So as you remember, some can be more lengthy, like fibers, where others will be more rounded in nature, and they will settle very differently based on the shape, the specific gravity, the size of those particles, surface properties, and slip factors. So these are all things that we will take into consideration. So surface properties, is it kind of like a pollen where it's more spiky, or is it more smooth? And these are things that we would consider when we think about how these will actually settle out. So on the right hand side of that slide, you'll see the particle itself, and the fluid drag forces and the buoyant forces will cause it to rise in nature, and then gravity is going to cause it to settle, and those can all be functions of its size and specific gravity and shape and whatnot. So on to slide 14. Very briefly, the aerodynamic equivalent diameter. This is a term that I just want you to be familiar with, because from here on out, I'm going to be calling it the AED. So the aerodynamic equivalent diameter of a particle is the diameter of the unit density sphere that would have the identical settling velocity as the particle. So basically what you're looking at here is what size sphere would it take to have the identical settling velocity of the particle that is in question. Okay, so we call that the AED. And that is slide 14. So on to slide 15. So discussing the AED further, it's a measure that we like to use for the behavior of a particle in the air, and it's going to be again a function of the particle's diameter, its density, shape, and surface characteristics, and determines size of deposition in the lungs. And this is where it really becomes important, because we want to look at how it's going to behave when it's actually entered into the respiratory tract of an individual. Is it going to settle into the trachea? Is it going to get picked up by the ciliary ladder, or is it going to be much smaller and penetrate further into like the bronchioles and things like that? And again, this is effects of air sampling characteristics, reference to spherical drops of water with identical settling velocity. So that's really what we're going to do, is we're going to compare it to other things and say, okay, how is it going to behave based on its comparison to a spherical drop of water with identical settling velocity. So it's a reference point. That's slide 15. On to slide 16, further consideration for the AED. Settling velocity of a test particle is measured and compared to reference of the particle itself. So again, you look at the particle on the far left side, that it has a different shape to it. So what they're going to do is they're going to correct it to a spherical shape, and then they're going to compare it to the water droplet corrected for density, and then these will have essentially the same falling rates, and then they can be analyzed. And again, this isn't something, obviously we can't do this in class, unfortunately. I do apologize that we are teaching this course online. It can be challenging, but I know that you've all done very well. I've enjoyed reading your labs and the work that you put into this. So again, I will always give you questions that are more theoretical in nature in regard to how these things actually play out in real life scenarios. On to slide 17. So we'll talk about particle size distributions. And when we look at slide 18, make sure I'm on the right slide. So we're looking at slide 18. This is a particle size distribution chart where you have the frequency, the percentage of the particles by count, and the particle diameter along the bottom there. So certainly we'll look at the X versus Y axis for these, and you'll notice that particle sizes of an aerosol are typically log normally distributed. Excuse me. So you're looking at the frequency on the y-axis and the particle diameter along the x-axis, and you'll see that the mean and the median are listed here. This is a histogram of the skewed particle size distribution. And again, this is just to kind of give you just a general idea of what's actually taking place here. This is a really terrible slide. I do apologize for that. And then we'll move on to slide 19, which is particle size distribution, which is a log transformation of the particle size distribution, which is normally distributed. And again, this is that standard bell curve where you're going to have the frequency percent of particles by count on the y-axis and the particle diameter along the x-axis there as well. So again, these are just for your review to kind of take a look at so you can have a little bit better of an understanding of how particles will behave. And then on to slide 20, which is the particle size distribution. And again, this probably looks a lot like an LD50 curve to you that we've discussed in the past, which essentially is kind of what you're looking at. You're looking at the percent of particles by count less than or equivalent to the indicated size on the y-axis, and the particle diameter, again, that's going to be on the x-axis as well. So this is a cumulative log normal size distribution in regard to how these are going to be indicated by size. And again, I know this is really challenging material, but as I'd mentioned before, these are things that are really designed for your review, and we will try to apply these to a more life-based scenario for you. So on to slide 21, particles and disease. This is section D. So this is really where I really want you to kind of focus some of your attention here. So we are currently on slide 22, and these are the diseases that have a cytotoxic effect. These are going to be the cytotoxic dusts that can be very problematic for individuals that are working in occupational settings, but also in personal life settings as well. These are going to have a direct effect on the lungs. So silica is going to cause silicosis. Asbestos is going to cause asbestosis. Coal dust is going to heavily affect coal workers, and again, just very challenging for individuals that work in these settings. Beryllium is going to cause berylliosis and chronic beryllium disease, but certainly very challenging. So silica, silicosis, very problematic. But certainly you tend to hear more about asbestosis. But silicosis is one of the reasons that when you drive past construction sites, you'll see signs that say no dust. And if you see dust, report it to this place, this telephone number. These are the things that they're concerned about. But certainly you've heard of black lung in regard to coal workers being exposed to coal dust, and a really challenging function of working in coal mines was that essentially that a lot of these people were dying from what was termed black lung. And certainly we do everything we can to protect individuals from these issues. So on to slide 23 with cytotoxic dusts. Knowing how much and where a dust will deposit in the lungs is important for risk determination, right? So again, your body has natural systems in place, like the mucosal lining in the trachea and the ciliary ladder that's designed to bring things back up and coughed out, and you have the cough reflex, which is going to allow you to cough these dusts back up. And these generally tend to be some of the larger particulate matter like PM10 and PM5. These things get tangled up. But certainly knowing that you're breathing in a lot of PM2.5 allows you to generate a risk determination for individuals that are working in these settings. So as you remember, with regard to the size of the particulate matter, it really is going to be generated based on how much energy it takes to generate that particulate matter. So a very high energy generation is going to make very small particulate matter. So that's when it becomes problematic. So like say for instance with diesel exhaust, when it's burned, it's going to make a very small particulate matter. And when you're breathing that in, it can be very challenging for an individual. Whereas with fibers like asbestos fibers, they're going to be larger in size, and they're going to deposit very differently in the lungs. And certainly will have a lifelong effect on those individuals that breathe those in. So it's kind of important to remember that knowing the size of particulate matter will determine where it's going to deposit in the lungs itself. So on to slide 24. These are some aerosol-related diseases. We'll discuss this briefly. Disease potential is a function of the chemical properties of the particle. So, what are its chemical properties? Site of particulate deposition in the respiratory system. So, that really, with diseases related to aerosols, we're looking at three specific regions, which is going to be the head region, the thoracic, and the respiratory region. And these are the things that we would consider to really kind of define the nature of the deposition in regard to the disease function for these specific components of aerosols. So basically, where is it going? Where is it going to stick within the body? And these are the things that can be challenging for aerosols. And also particle clearance and path destination. So where's it going to end up? So some aerosols can be very problematic because they may have a destination that is, perhaps the bronchioles or even the alveoli. These things can end up in this path, this destination, and then it can be very problematic. So the path that it takes, like with regard to asbestos, asbestos is going to be breathed in. It's going to be deposited in the lungs, but it's also going to pass through large intestines, small intestines, colon, things of that nature, and it can be problematic in all those different areas with regard to its path itself. So on to slide 25. This is the regional particle deposition. This is just an image here. So you have inhalable dust that is going to deposit in the upper head region. So that's that nasopharyngeal cancer that we talked about in regard to workers that are working with wood dust. And you also have the thoracic dust, which is depositing in this area here with the trachea and things of that nature. And then the thoracic region where you see the respirable dust that's going to end up getting much lower. So these are going to be like the PM 2.5 that's going to come from diesel exhaust and things like that can be very problematic. Site of particle deposition, again, you have the percentage deposition on the y-axis, and you have the aerodynamic diameter on the y-axis here, or excuse me, on the x-axis. So basically what you're looking at is the size of the diameter of the particle itself and where it's going to be deposited. And this is kind of it's a little bit of a busy graph, but you certainly can see that the deposition is related to the size of the particle based on its the aerodynamic diameter. So on to slide 27, inspirable, inhalable dust definitions. So you have the percentage of penetrating on the y-axis and the aerodynamic diameter on the x-axis here. And this just kind of gives you an idea of the percentage that are going to be penetrating. And certainly you can see that there's not much change essentially between the 20 and the 100 components of the aerodynamic diameter. And then on to slide 28, the thoracic dust definition. So you have percent penetrating versus the aerodynamic diameter along the x-axis again. But you can see some differences here. So when you look at this, with thoracic dust, you're definitely seeing a difference in regard to its penetrating power. And on to slide 29, this is respirable dust definition. Again, percent penetrating versus the aerodynamic diameter, excuse me. And let's move on to slide 30. So old particle size conventions. So you have non-respirable versus respirable. So with non-respirable, which is greater than 10 micrometers AED, this can be breathed into the nose or the mouth, and it's going to penetrate the head airways and enter into the lung airways, versus respirable fractions at less than 10 micrometers AED. This is going to penetrate beyond the terminal bronchioles and into the gas exchange region. That's one of the reasons that anything that's less than 10 micrometers in size is so much more dangerous. So again, it's going to exceed the terminal bronchioles, and it's going to go into that region of the gas exchange, and that's why it's so dangerous. And when it begins to choke up these locations, that's where you really start to run into problems with particulate matter. So with non-respirable, again, this is going to enter into those airways, it's going to enter into the lung ways, it's going to enter into the head, the nose, the mouth, but it's not going to be able to be introduced into that gas exchange region at less than 10 micrometers. So again, you can see, greater than 10, yeah, it's a problem, but it's generally going to get caught up with these natural mechanisms for the body that are designed to expel them, where with the respirable fraction, less than 10 micrometers, they can be very dangerous, and they're going to enter into that gas exchange region. So with new particle size conventions, inhalable fractions are going to be less than 100 micrometer AED and can be breathed into the nose or mouth. With the thoracic fraction, it's going to be less than 25 micrometers, and that can penetrate the head and enter into the lung airways. So not ideal, like when you consider things like asbestos. Asbestos is going to, fall into this category, into the thoracic fraction. And then you have less than 10 micrometers AED, which is the respirable fraction, which can penetrate beyond terminal bronchioles to the gas exchange region. So this is essentially what we're going to call the new particle size convention versus the old particle size convention. The new particle size convention is much more updated, and this is generally what we tend to look at, and we take this into consideration. So new particle size conventions, outdoor or ambient air pollution. So again, with ambient air pollution, this is going to be the air that's around you. Recommendations by the EPA. So particulate matter at less than 10 micrometers. This is going to be PM10. Particulate matter, which is less than 2.5 micrometers, is going to be PM2.5, and PM2.5 is really what we're focusing on as far as being much more dangerous. But as you know, with prolonged exposure, things like PM10 can be very dangerous as well and can create a lot of problems for these individuals. So this is roughly going to correspond to inhalable and respirable dust. Let's move on to slide 33, which is section E. This is mechanisms of particle deposition. So with mechanisms of particle deposition in the lungs, we're going to be looking at inertial impactions, which are going to be a function of particle velocity and their mass. So how are they moving? What is the velocity? How fast is it moving? And what is its mass itself? So the size, the weight, these are all going to be important components. Certainly the how fast it's moving and its actual weight is going to be what we're going to look at in regard to inertial impactions. And then there's the interception component, which is a function of the particle's diameter. So what is its actual diameter? And that's going to directly relate to its interception. How is it going to be picked up? So on to slide 35. Sedimentation, which is a component of gravitational settling. It's a function of the particular velocity and its mass itself. So again, how fast is it moving, and what is its actual weight, its mass. And then diffusion is going to be a function of the particulate diameter, its concentration, its velocity, and its distance. So how is it going to be diffused? So as you remember, we talked briefly about this process upon which it can enter into the gas exchange, and is it going to be diffused? And that's a function of its particulate diameter, its concentration, velocity, and its distance as well. So sedimentation, is it going to settle? And diffusion, is it going to be diffused? So I'm hoping these terms are not too outside of your common lexicon for this class, but certainly ask me any questions that you have. So let's move on to slide 36, mechanisms of the particle deposition in the lungs. So as you remember, we have the inertial impaction and we have gravity that's affecting it. So you see the alveoli, those little clusters of grapes at the ends of these bronchioles. So if we talk about inertial impact, we're talking about the process by where a particle moving in a gas stream is unable to remain in the gas stream, and the gas changes directions, right? So you see these curves, and when they change a direction, Is it going to fall out? Is it going to be continue to move in the stream, or is it going to be unable to move? And that's that inertial impaction. So as it changes directions, it can potentially be picked up, or will gravity allow it to continue on? And this is a result of the particulate striking a stationary object, like the surface of the respiratory system, directly in its path, and then it's going to be removed from the air. So as it's turning, it can potentially strike that solid mass, and it can be picked up. But again, with PM 2.5, the inertial impaction is going to be much more diminished, because it's so small in size. It's going to be able to move with those changes in direction, and then it can be deposited into the alveoli and into the gas exchange. So inertial impaction is something that we're going to look at based on certainly the velocity and the mass of these materials as they're moving through the respiratory tract. So on to slide 37. Then there's interception, which is a process whereby a particle moving in the gas stream remains in that airstream, but because it has specific dimensions, it's going to strike a stationary object. It's like the surface of the respiratory system, and then it's going to be removed from the air. So interception is where it's going to be picked up, and that's kind of ideal that it gets picked up before it enters into the lower components of the respiratory system. So again, it can be intercepted by the ciliary ladder, it can be intercepted by the mucosal lining, and those are generally going to happen with things like PM10. On to slide 38. Mechanisms of particle deposition in the lung. Again, and this is sedimentation. This is a process by which a particle in the airstream is pulled downward by gravity until it strikes that stationary obstacle, so like the surface of the respiratory system, and is removed from the air. So again, the gravity will have an effect on sedimentation, especially in regard to PM10. Because it's larger in size, it has more mass, generally it's going to get picked up by the respiratory system, hopefully by that ciliary ladder or the mucosal blanket. And then on to diffusion, and this is slide 39. This is the process by which the molecules of two or more substances, usually very small particles, have some molecular characteristics which is going to gradually mix as a result of random thermal motion. And this is going to strike a stationary obstacle like the surface of the respiratory tract and be removed. But with regard to diffusion, this is that process that we really get concerned with. So you can see where it is here on the diagram on the left-hand side. So that you can see that component where these very small particles are going to gradually mix, and this is through that process of random thermal motion, and they're going to strike that stationary obstacle. But again, diffusion is that process where it's going to be much more penetrating, and it's going to get further, and it's going to create problems for these individuals. So this is a very, very quick overview of particulate matter. And again, as I had mentioned before, we're going to try to, in regard to the lab, we're going to apply this in a more theoretical component. So we'll have a conversation. Certainly, if you have any questions or concerns, make sure and send me your messages. Judging by your responses to the labs in the past, you've done a very great job of applying these features. But again, think about how we utilize protective equipment, personal protective equipment for our staff and for ourselves when we're working around things like fumes and dust and things of that nature. So obviously with larger components like PM10, a dust mask may work, or a NIOSH N95 respirator may work very well. But when we're dealing with things of a much smaller nature like PM 2.5, maybe we increase our protection with our personal protective equipment. So those are the important takeaways, that you kind of have an understanding of particulate matter, how it can affect individuals both outdoors, in ambient air situations with the air that's around us, but also in an occupational setting as well. So I'm hoping that you get a little bit out of this. And again, as I'd mentioned before, how I test, how I write the labs, and I hope there really aren't any substantial questions or concerns with regard to the material. But if there are, always send them my way. I'm always happy to help you in any way I can. And don't forget, your paper is due November 25th, and your presentation is due December 2nd. So do keep that in mind. Make sure not to leave those till the last minute. And I hope that everybody's doing great. Keep your questions coming to william.vandyke@csusb.edu. And I look forward to another wonderful round of labs from all of you. So thank you so much and have a great week.